squared e to the alpha x sine beta x. Am I allowed to do that? If I have an equation, I can add something to both sides, right? Because this was a minus, I can add it, and it goes away completely, doesn't it? Over here, think about this. Just pause for a second. If I ask you to take, I don't know, one pair of glasses and add 3 pairs of glasses, you would have 4 pairs of glasses, right?
You need a pair of glasses.
I do. I have readers all over my house, but I can never find them when I need them. Okay, so I have one integral, right? One of these integrals, and I need to add to it how many of them? How many of these integrals is this? This is one of these integrals, right? How many of these? No. Alpha squared over beta squared. That's how many of, see, if this was a 2 in front, you would say one of these plus 2 of these is 3 of these, right? So you need to take this coefficient and add this coefficient. That's how many of these integrals you have. That make sense to you? So here's where I am. On the left side, I have 1 plus alpha squared over beta squared. That's how many integrals e to the alpha x sine beta x dx I have, right? That's how many of them I have. Look, if I would have given you numbers to start this problem out, right? If I would have given you nice numbers, like let's just say, I don't know, let's just say I gave you that this was 1 and that was 1, right? Then this would just be 1, wouldn't it? And then you would have 1 plus 1, you would have a 2. But I gave you a harder problem with alphas and betas just because now you feel like this makes you feel more mathy, doesn't it? To use all these weird things? Okay. And we don't want to be intimidated by these things, right? We want to be comfortable working with them. That's how many of I have, right? And that equals whatever was left here. That, right? And notice that what's left has no integrals in it, right? It's just an expression. E to the alpha x cosine beta x plus alpha over beta squared e to the alpha x sine beta x. Yeah, that's all of it, right? I'm going to get rid of this. You have this. Right? That's it. So the original problem, I want to know what this is, right? I want to know what this is. So I don't actually want this here. So what can I do with it? Divide through. This is just a number, right? So I'm going to divide this by that number, divide this by that number, divide this by that number. It's going to look weird, but that's what I'm going to do. So I'm going to have, this is going to be my final answer. E to the alpha x sine beta x dx equals, okay, I'm going to take this entire expression and divide by that. There's so many different ways you can write this. I don't even know how I want to write it, to tell you the truth. How about I just do it like this? Negative 1 over beta e to the alpha x cosine beta x. I'm just going to take that whole expression and divide it by 1 plus alpha squared over beta squared. And then plus alpha over beta squared e to the alpha x sine beta x over that thing I divided by, 1 plus alpha squared over beta squared. This is my answer, with exception, I've forgotten one thing. Plus c. See, I need to remember that this is an antiderivative. The way I got it was tricky because I added the integral on both sides, so I never really had an opportunity to do the plus c. So I have to remember that, you know what, this is the antiderivative, so I have to do plus c. Now look, there's a lot of different ways we could algebraically mess with this and clean up, but this right here is a valid answer. So this is a weird implementation of integration by parts. For a lot of students who've never seen this before, this is like, whoa, okay, I didn't even know we could do that, right? Where you could do the integration by parts a couple of times, and then the thing you're looking for appears on the right side, and then you can add it to both sides, and then you can get the integral that way. All right, that's weird, yes? Very different than what we've done so far, yeah? All right, let's do another one.
So you just do it until you get the same.
Yes, but the thing that told us that that might happen, now in retrospect, thinking back to the beginning of the problem, we knew that there was no clean choice for u or in dv for integration by parts. But now that you think about it, I know that every time I do integration by parts, that's going to stay the same with some constants, right? Like alpha would come out or something. That's going to cycle back and forth between sine and cosine. So eventually, in integration by parts, I'm going to get this expression again somewhere down the road. Does that make sense? So that's kind of the motivation. Yes?
Would it have worked if we used sine instead of
Yes. So in the very beginning, I chose u to be e to the alpha x, right? And I chose dv to be the sine beta x. If you did it the other way around and chose u to be the sine beta x and the dv to be the e to the alpha x, it would still work. Yes?
So do we only do this moving the whole expression over to the other side added only when we get back to the original?
Yeah, you have to wait till you get back to the original. Absolutely. And not every integral works this way, right? Like most of them just end, right? We can actually find the antiderivative.
Did it twice to go back to the original?
For this problem, it took 2 iterations of it, yes. Because of the sine and cosine, the nature of the sine and cosine, the first time we did integration by parts, the sine became a cosine. The second time, the cosine went back to a sine, right? All right, let's do another one. How about this one? Be careful. This is not this integral. That's not this. Okay, if it were this problem, what I would do is use properties of logs and pull the 2 out first, completely out of the integral. And then I know the antiderivative of natural log because we did that a couple of classes ago, so I'd be done. But that's only if the two is acting on the argument here that you can pull that out. Here, the 2 is acting on the entire logarithm, right? So you don't have that property. Well, any ideas?
Let's make u the entire natural log of x, and then dv will be dx.
So you're thinking let u be all of this, or you're doing integration by parts, and you want u to be all of that, and then dv to be that. I saw someone else. You want to look at it as 2 logs, and then do one of them be u, the other one dv. So do y'all see there's kind of 2 ways we could approach this? So let's do a show of hands. How many of you want me to let this whole thing, let me show you what I'm doing. I need to choose u here, and then dv. Show of hands. How many of you want me to choose this whole thing for u, and then I'd put a 1 for dv? Okay, how many of you want me to split it into 2? And then let this one be u and that one be dv. Okay, that's overwhelming that way. Let's go this way. I'm not saying doing it the other way it won't work, but let's go with this, all right? Because that's what everyone kind of feels like they want to do. All right, natural log x dx here. Look, whenever you do this table, the dx has to go somewhere, right? The dx has to go somewhere. It has to go with the dv, all right? You can't put it up here with the u. Okay. What now? Fill out the table, right? So what's the derivative of u? 1 over x dx, and then the antiderivative of natural log x. I told you could put that in your formula sheet, right? So we don't have to go through that again. This is x ln x minus x, right? That was what we had done already. Yeah? Okay, so here's where we are. We have this equals, right? This equals ultraviolet, right? Ultraviolet. So this times this. I'm going to write that down. Natural log x times, I'm going to put it in parentheses, natural log x minus x. Okay, so that's ultraviolet. Minus a little space integral. And then voodoo. When I look at voodoo, here to here, I don't see any constants that can come out, right? This doesn't have a constant other than 1, right? That doesn't have a constant. So I'm just going to have to multiply those two together. Let me do that on the side. What would voodoo be here? Wouldn't that be x natural log x minus x, multiply that times what? 1 over x dx. So when you pass a 1 over x through here, doesn't it just kill off that x and that x? So in here we should just have what? Natural log x minus 1 dx. Can you find the antiderivative of that? Yeah, this should be no problem, right? Subtraction, I can do them piece by piece. What's the antiderivative of this? Well, we know that, right? We actually used it right there. So we already know the antiderivative of that. And the antiderivative of 1 should just be x. So we're there. So this would be natural log x times x natural log x minus x minus, okay, antiderivative of that would be x ln x minus x, right? I'm going to do this. Let's put that minus let's put everything in this integral in a bracket so we can distribute our signs properly here. Okay, so this is minus, and then this integral becomes the antiderivative of that, which is this, and then minus the antiderivative of 1, which is x, right? And then plus c. Let's clean it up. I think that does clean up a little bit. What do I want to do here? I'm going to distribute this through, negative through. But I'm also going to distribute the natural log through. So my first term is going to become x natural log of x times itself. So x natural log of x squared. That's this times this. And then I'm going to do natural log of x times negative x. So I get negative x natural log x. And then I have negative times this, so minus an x natural log x again. And then these two together is negative 2x, right? And then distribute a negative, so plus 2x plus c. And then these two come together, yes? Those are the same thing. So a final clean answer would be x natural log x squared minus 2x natural log x plus 2x plus c. There we go. I feel like checking this. I feel like taking the derivative. Okay, can I do that? Let's just check to see that this is the right answer. If I take derivative of this, I better get back this right here, right? Or this, either one. So if I do a quick derivative, product rule here, right? I'm going to have two product rules, and then this one, well, I'll just put that here. That's plus 2, right? Right here. Okay, product rule here. Derivative first one is 1 times the second one, plus derivative of natural log of x squared is chain rule. So 2 comes out first, natural log x, times the derivative of what's in here, 1 over x, times the first function, x. That's my product rule on the first one. Minus, now I'm going to do some parentheses. The product rule, I'm doing product rule right here on this. Derivative of 2x is 2, natural log x, plus derivative of natural log of x, which is 1 over x, times 2x, and then plus 2. That works. because this is just natural log of x squared plus these x's cancel, so I get 2 natural log x. Then this right here, the negative goes through here, so I have minus 2 natural log x. And then this goes through here, the x's cancel, I get minus 2 there. And then I had plus 2 down here. And then this is gone, 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 gone. You get natural log of x squared. I went through that quick, but it does check, all right? Do y'all want to try it the other way? A few of you raised your hand. Do y'all want to try it the other way? Let's see. Maybe it's easier. Maybe it's harder. We should know pretty soon. Did anyone try it? Did you? Anyone who wanted the other way, try it? No? Okay, let's do it then. Let's just see. So we can let natural log x squared be our u, and then let this be 1 dx, right? That's another choice we would have had. The derivative of this would have kind of sucked, right? A little bit? It'd just be chain rule, right? 2 comes out, 2 natural log x times 1 over x dx. Y'all following that derivative? Yeah? What's the antiderivative of 1? X. Ultraviolet. X, natural log of x squared, right? That's ultraviolet. Minus space integral voodoo, these two. Can I pull out any constants from these? A 2? Okay, look at what voodoo looks like. I'm pulling the 2 out, so ignore the 2. If you take this and multiply this, right? Natural log x times 1 over x times x. The x cancel and all you get is natural log, right? Simple integral. X, natural log x squared minus 2. Now the antiderivative of that is x, natural log x minus x plus c. Same answer. Isn't that the same answer? Distribute the negative 2 through and you get back this. Which one was easier in your opinion? The second way? Got it both ways though, right? Okay, good. Any questions? I'm just going to continue doing problems. I mean, it would be nice if we had like 6 hours today and I could do some problems, have you do some problems, but you have to go home and do problems, right? I need to kind of show you enough of the little things that can happen for you to hopefully feel comfortable. But this one. Secant cubed x dx. If it was secant squared, you'd be done, wouldn't you? Because the antiderivative of secant squared is tangent. But it's secant cubed. So
Is that the argument? It's secant cubed x.
the secant cubed x, yep. Well, split it up, how? You want to do secant squared x times secant x? But you could bring cosines in as well if you wanted to, but look at that right there, just as that is. Could we do integration by parts with this? What would you choose for your u, and what would you choose for your dv? You kind of only have one choice here. Well, I guess you don't, but what makes the most sense to you? Do this one to be your secant squared, because you know the antiderivative is tangent, right? And then let this one be your secant, because you know the derivative of secant is secant x tangent x from Cal 1, right? So it's worth a shot, yeah? I mean, so the derivative of secant x is secant x tangent x dx. Antiderivative of secant squared x is tangent x. All right, ultraviolet minus voodoo, right? So we've got equals ultraviolet. Okay, that's just secant x tangent x minus a little bit of space there. Are there any constants that I can pull out of voodoo? No. What is voodoo? Secant x tangent squared x, yeah? Ugh. That does not look good, does it? Secant x tangent squared x actually looks kind of bad, yes? See, this isn't like the e to the alpha and the sine, because it's not like the e staying the same and the sine is oscillating back and forth between cosine and sine, right? As we integrate, the antiderivatives of these don't switch back and forth, right? It became, look at these two things. These are different, right? Yes?
Couldn't you like split the tangent and do secant tangent, like the antiderivative of secant tangent, and then you, oh wait, no, because then you'd still be multiplying it.
No, I think I could peel a tangent off and do secant tangent and then separate a separate tangent. I could do that, right? I think what you're saying is, can you rewrite this as secant x tangent x times tangent x, right?
Yeah.
Dx. And then go ultraviolet minus voodoo on this one, like integration by parts, where you let this one be your dv and that one be your u. Is that kind of what you're getting at?
Kind of, I just got kind of like confused in my head, so I stopped.
No, I'm going to write this down. Don't write this down. I'm going to write this down, okay? Do y'all agree we could do this? Yes? And then I could let that be my dv. I'm doing a second integration by parts. I could let this be my dv and let this be my u, right? My u and my dv. All right, is that not the opposite of this though? Do y'all see it's the opposite of what we just did? Like, so if I do this to here, I'm going to get secant squared. And I do this to here, I'm going to get secant, right? And when I do ultraviolet minus voodoo, what you're going to wind up getting is everything's going to cancel out. And you're going to get this as your expression. You're going to get secant cubed back. So when you do integration, when you do this integration by parts, letting u be secant x, dv be this, if you do integration by parts a second time, don't reverse that process, because you're just going to go right back to where you came from. So it's good to think that way, but it's not. We want to avoid that in particular. All right, so I just said a second ago that part of this is, you have to, I would love to spend 6 hours in here and we're all having fun and we're having margarita machine in the corner and we're just doing integrals all day long, right? I have to show you certain things, right? That way you kind of know, like, okay, when I'm doing my problems, I remember he did this once, maybe I can do this on this problem, right? There's no cookie cutter way though. Are you getting that in this class? There's no like, here's the way you do every integral, right? It's not like that. You have to just try something. So here it is. I'm going to go back to pre-cal, and I'm going to go back to a Pythagorean identity. I have a Pythagorean identity in pre-cal that says tangent squared x plus 1 is equal to secant squared x. You remember that? Yeah. You have 3 Pythagorean identities. The most important one is sine squared x plus cosine squared x equals 1. But there's 2 others. This is one that you should get comfortable with, very comfortable with. Right? We're going to need this a lot in this class in the next few weeks. So that identity, I can solve this for tangent squared, can't I? If I try and isolate this, tangent squared x is what? Secant squared x minus 1, right? Do y'all know where these are?
Page 2.
Page 2. Right there. See it? Under cotangent. This is the one everyone should know. That's the one I'm referring to. Now they have the 1 and the tangent squared backwards, but it doesn't matter with addition, right? So wherever I see tangent squared, I can replace it with secant squared x minus 1, right? Let's do that. To save time, can I just erase this and stick it in here? Okay, this is going to be secant squared x minus 1. So as I'm thinking about this, I'm like, why do I want to do that, right? Why would I want to do that? Well, if I do that, I distribute through that first distribution, what am I going to get? Secant cubed, the original integral, right? The original integral. And aren't I subtracting this? So I'm going to be able to add that integral to the other side, just like we did with the e and the sine a second ago. Now I also have to distribute through to here, right, which is going to give me a secant x, but I know the antiderivative of secant x because some dude spent like his whole life trying to figure out what to multiply, right? I showed that to you in the very beginning, that first problem we did. So I can handle secant x by itself, and the secant cubed can go back to the other side. So I'm going to continue this way. Tricky yet clever, yes? Secant x tangent x. Okay, I'm going to break this up. Minus the integral of secant cubed x dx plus the integral of secant x dx. Can you follow what I did there? Secant goes here, secant goes here. So I have secant cubed minus secant, right? But I'm subtracting. So I break into two integrals. The first one's a minus, then the double negatives give me the plus. Do you all see that or no? Okay, I'm going to go over here. Here's where we are. The original problem is the integral secant cubed x dx. Here's where I am. I'm right here at this line. I have equals secant x tangent x minus the integral secant cubed x, very happy to see you, plus the integral secant x dx, right? That's where I am. Do y'all see that if this was a plus, I wouldn't be able to go anywhere from here, right? If that was a plus, then the most I could do is what? Subtract it on both sides. And if I subtract this on this side and subtract it here, it goes away. And you don't get anywhere because you've eliminated the integral. It's very important that this minus sign is here so you can add it. Which means if you mess up a sign, it's over, right? So be careful. So plus this integral on this side, plus the integral on this side. These go away, right? How many of these integrals do I have? Two of them, right? It's better than the 1 plus alpha squared over beta squared that we had a second ago, right? I have two of those integrals. I just erased it. I should have just left it there. I have two of these integrals equals the other side, right? What's still on the other side? Secant x tangent x, right? That's this. This is gone. And then I need the antiderivative of that, right? Which we know we could go to our formula sheets or just look at the first problem I did today. This is plus natural log secant x plus tangent x. And I may as well just put my plus c now, because I technically have taken an antiderivative at this point when I did the antiderivative of secant. One more step. Divide by 2, right? Divide by 2. So I'm going to have integral secant cubed x dx equals, when I divide this by 2, same as multiplying it by a half. So I'm going to put 1/2 secant x tangent x plus, same thing with this. Dividing this by 2 is the same as multiplying by a half. Natural log absolute value secant x plus tangent x plus c divided by 2 is still c. It's just a constant. It doesn't matter if you divide a constant by 2, it's still a constant. Yes? Because you had 2 of these, right? When we added this integral to both sides, I had one of them plus one of them, that's 2 of them, right? But what was the original problem asking us for? The original problem was asking us for that, right? Not that, that. So I don't want this 2, so I just divide by 2. Divide this side by 2, it goes away. Yes? Over here, that integral was the first problem we did today, right? So I just went straight to the answer. Any other questions? Yes?
If you have second squared plus 1, and they have this size plus, would you have?
There was it's not on the board anymore, but, well, I can show it real quick. It was, we had minus the integral, then it was secant x, and then we turned the tangent squared into secant squared x minus 1, right? This, and then when I distributed through, this became secant cubed x minus secant x, right, in this integral with a minus in front dx. Negative comes here, and then there is where it became the plus. Got it? How many have I done? 1, 2, 3. Done like 4? It's only taken me an hour and 5 minutes. I have 8 of them. So let's see if we can get to some more. This next one's kind of interesting, looking at least. Am I boring you? Should we stop? Should we keep going? Are y'all hanging in there?
I'm waiting for like the arctan one.
Arctan x?
Yeah, where it's like you have to do integration by parts and integers.
I'll do that next. I'll do one of those. I'll do arc sine or something instead, though.
So, our full answer is going to have the integral in the beginning of it equaling to all the crap we just did.
Well, your answer is the right side. But whenever you have that problem like I just showed you, where the thing you're looking for shows up on the right side again, you need to write it as an equation so you can work with it as an equation and add it to both sides. Yeah, but ultimately your answer is just the right side of that equation, because that's the antiderivative.
So let's make you sine of natural log x.
Yeah, so if we're going to do integration by parts here, yes.
Can you ever take the derivative of dx?
Could you ever take, so let u be dx? Is that what you're saying?
Could you ever take the derivative of dx?
Yes, you would get a second derivative, but it wouldn't